All right, so in this problem, we have two gray whales that are swimming towards each other. And one of the whales, the first whale, sends out a signal at 1200 hertz. And that signal then travels towards the second whale, who picks up the signal. Now, due to the motion of both whales, the second whale will receive a frequency that is a little bit different from the 12,000 hertz original value. And then as the second whale reflects the signal back to the first whale will receive the echo. And the frequency, once again, is shifted because the echo is bounced off a moving object, which is the second whale, and the receiver, which is the first whale, is also moving. So you also want to know what is the received signal, received frequency of the echo from the first whale. Now, in the last part of the problem, suppose there is an ocean current, okay, that moves at 25 miles per hour at 30 degrees north of east. How does that affect the result of the echo frequency? So let's see how we do this problem. All right, let me do a new share. So now I have a picture of the situation. The first one moving towards the east at V1, which is 50 miles per hour. I've changed that to 80 kilometers per hour. And the second whale moving towards the first whale, that is moving west at a speed of V2, which is 40 miles per hour or 64 kilometers per hour. And the speed of the medium, which is the speed of, actually the speed of sound in the medium, which in this case is seawater, is 5,470 kilometers per hour. All right, so let's look at the first problem. What frequency does the second whale get that come from the first whale? The original frequency, as you know, is 1200 hertz. Okay, and here the signal received by the second whale is obviously Doppler shifted due to two reasons. One is the source, which in this case is the first whale, is moving towards it, and that will increase the frequency. And secondly, the observer, which is the second whale, is moving towards the source at speed V2. That again increases the frequency. So now I have, if the original frequency is called F, and the frequency heard by the second whale is F prime, then I have F prime equals F times a factor. This factor has a numerator and denominator. The numerator is due to the motion of the observer, so it's V plus V observer, which in this case is V2. And the reason why it's a plus sign is because the second whale is approaching the first whale, and that tends to increase the frequency. That's why it's a plus sign. Okay, so that makes F prime greater than F. Now, divided by the denominator is due to the motion of the source, as you know, so it's V, and here is V, the speed of the source, which in this case is V1. Should we use a plus or minus sign between V and V1? Well, again, you look at whether or not this motion of the source increase the frequency received by the observer. So F prime is greater than F due to the motion of the source, because the source is approaching the observer, and that means we have to use a negative sign. Okay, that's how you increase F prime due to the motion of the source, right? So you have 1200 hertz, and you have, just plug in the numbers here, speed of the sound in the water, 5,470. Everything is in kilometers per hour, so I don't have to write the units anymore. V2 is 64, and then divided by 5,470 minus V1 is 80. Okay? So the factor in the parentheses is slightly greater than 1, and if you do the algebra, you find the answer to be 1,232 hertz. So there is a change, there is an increase in frequency of 32 hertz. Okay, So that's the first part of the problem. Now, the second part of the problem, what is the frequency of the echo heard by the first wave that's bounced off the second wave? Well, we already know the second wave receives a frequency of 1,232 hertz, and that's f prime. But that is not the frequency f double prime that is heard by the first wave as it bounces off. So what is f double prime equal to? Well, it starts out with f, but there is another Doppler shift for two reasons. One is the echo is the source, right? The echo is bounced off of the second wave, and the second wave is moving towards the first wave. So the second wave is now acting as a source, and that source is moving towards the first wave. So, and that tends to increase the frequency. So in the denominator, which has to do with the source, I have v minus the speed of the source, which in this case is the second wave, speed of the second wave. So it's v minus v2. And also because the observer this time is the first wave, right? As he receives the echo. So the observer is moving towards the source. So that again tends to increase the frequency f double prime. So that is v plus the source, the speed of the observer, which is v1. Okay. Now you take a close look, you find these two parentheses in the first part and second part, they're different. Okay. It's no longer v2 in the numerator and v1 in denominator. It's the other way around. So the factor will be a little bit different. So let's find a numerical value. F prime, which is 1,232 hertz. Okay. And this time, the factor involved is 5470 plus v1, which is 80, and divided by 5470 minus 64. So the answer is, once again, involves a factor a little bit greater than 1. So the answer this time is 1,264 hertz. Okay. So the first wave will hear an echo with a high frequency higher than that heard by the second wave. All right, now let's look at the last part, which is the most interesting part, probably. If the ocean has a current speed, so the ocean is actually flowing, okay, and the ocean is the medium, right? The medium. The entire Doppler formula we've been using so far assumes the medium is at rest. There is no speed of the medium. Otherwise, the formulas are not valid. So what do? Well, as we saw in the video lecture, the strategy is that we are going to make sure the medium does not move so that we can once again apply the Doppler formula we have already learned. And how do you make sure the medium doesn't move? Well, you have to switch to a new reference frame which moves along with the medium. And in that new reference frame, there is no motion of the medium. Now, here in this case, the medium has a speed, has a velocity that's in this direction. We call this velocity u, okay? And this u is 30 degrees north of east. So 30 degrees, theta equals 30 degrees. And u equals, numerically, it equals to, let's see, it equals to 25 miles per hour. And let's see how that factors into the calculation. Well, first of all, when you look at the Doppler shift effect, everything happens along the line connecting the two waves, the source and the observer. Okay, in this case, it's the x-axis, right? If there's any motion of the source, of the observer, or even the medium that is perpendicular to the x-axis, okay, so say the whale moved in a y direction, does that change the frequency? No, because if the source observer move along the y direction perpendicular to the line connecting the two objects, then this motion will not allow the observer to cut into the waves coming from the source, or it won't compress the wavelengths of the source. Okay, so it's not going to change the frequency at all. Similarly, for the speed of the medium, it's the same idea. All we have to consider is the velocity of the medium along the line connecting the two objects, the source and observer. So in this case, we only have to consider the x component of u, the velocity of the ocean current. Okay, let's do that. Let's find that component. Let's find that component. So that is ux. Okay, ux equals u times cosine 30 degrees. Okay. And you can find numerically what that equals to. Okay, u is 25 miles per hour, multiplied by 1.6 to get kilometers per hour, and then times cosine 30 degrees. You do your algebra, you find the answer to be 34.6 kilometers per hour. So as far as the x component of the velocity of the medium is concerned, the ocean current is flowing eastward at 34.6 kilometers per hour. Now, we want to switch to a new reference frame in which ux equals 0. That's the whole idea, right? In that new reference frame, so now imagine you're flowing along with the ocean current eastward at 34.6 kilometers per hour. In your new reference frame, how fast is the first whale moving? Well, the first whale, because ux and v1 are along the same direction, the observer moving along with the current will see a reduced speed v1, right? So v1 becomes v1 prime, which is v1 minus ux, right? And so that is 80 minus 34.6, and the answer is 45.4 kilometers per hour. And similarly, look at v2. Now, the current is flowing towards the second whale. As the second whale moves towards the current, and therefore, in the reference of the current, v2 will be greater than before. v2 now becomes v2 prime, and that is v2 plus ux, right? And that is 64 plus 36. 34.6. Okay, and the answer for that is 98.6 kilometers per hour. Right now, you can now use the formula that you've been using for part 1 and part 2. The only difference is that whenever you see v1 should replace by v1 prime, and whenever you see v2 should replace by v2 prime. All right, so now they're looking for part B, F double prime. What is the frequency of the echo heard by the first whale with the ocean current? So I'm looking for V2 F double prime again. So F double prime, the formula is the same as before. It is F prime times this factor here. This factor is V plus, instead of V1, I have V1 prime. Formula is the same, just replace V1 with V1 prime. And V2 is V2 prime. Right? And F prime itself, looking at part 1, F prime itself is F times V plus V2 prime, not V2 this time, divided by V minus V1 prime instead of V1. And then don't forget this existing factor of V plus V1 prime and V plus V minus V2 prime. Okay, now that you look at the last two parentheses, they don't exactly cancel each other out, do they? Right, and so you can plug in the numbers here now, 1200 hertz. Okay, and then all the factors, all the numbers, 5470 plus V2 prime is 98.6 divided by 5470 minus V1 prime, which is 45.4. Okay, now the second factor, V, which is 5470 plus V1 prime, which is 45.4. And then lastly, 5470 minus 98.6. Okay, and what is the numerical value? If you did that, the answer turns out to be 1265 hertz. Very close to the result of part 2, which is 1264. But the formula is different. Okay, so the result is also slightly different. And again, the whole idea of the last part is that you want to switch to a new reference frame, which moves along with the ocean current. In that new reference frame, the current has no speed. So the medium is once again stationary, which allows you to use the formulas we've derived before with stationary medium. And also understand that any motion that's perpendicular to the line connecting the source and medium is irrelevant. You only have to consider the component of the velocities along that line. All right, so that's how we do this problem. This problem pretty much includes all the tricks that we need to know about acoustic Doppler shift.